So we want to talk a little bit about power factor and how it relates to impedances and power. Okay, so power factor. So we see here that this is related to our complex power. So our complex power has real power along the x-axis and then reactive power. And then the apparent power is the hypotenuse or the magnitude of these two. And then we have the angle between the two, and the angle is going to be related to the power factor. So we basically break this up into a complex, J equals P plus JQ. And we see here that the power factor is equal to the real power, or P, over the magnitude of our complex power, or our apparent power. Okay, let's review this a little bit more. So here is our complex power is defined as V times I conjugate. Okay, and this assumes that our voltages and our currents are in RMS values. Otherwise, we'll have an extra 1/2. We're going to be doing RMS, so we just has V times I conjugate. So if I can plug in for the I conjugate or the V, using Ohm's law, then we get this main equation here. So it's the magnitude of the current times Z, or the magnitude of the voltage divided by Z conjugate. Okay, so now we're going to see how we're going to use these to get it to work out. So let's look at a basic circuit. So a basic circuit has some voltage and it has some impedance. Okay, and then we also have some current right here. Okay, so what we're going to do is we are going to look at our basic equations. So just to review what we had before, we have S is equal to P plus JQ, and we have this triangle right here, and then this is P, this is Q, and then this is S. And so if I look here, we see that this is going to be equal to I magnitude squared times R, and this is going to be equal to I magnitude squared times the X. And then the magnitude of this is going to be equal to I magnitude squared times Z magnitude. Okay, so now let's look at how all this relates into the power factor. So if I look at my power factor, which is equal, this is our theta, is equal to the cosine of theta, which is going to be equal to I magnitude squared times R over I magnitude squared times the magnitude. So this is equal to R over Z magnitude. Okay, so then we also want to get our complex part. So what we want is we want the sine of the angle. And so in order to get the sine of the angle, we're going to use sine squared of theta plus cosine squared of theta equals 1, which means that the sine of theta is equal to 1 minus cosine squared of theta. So we can use this to find the x part. So we have 1 minus power factor squared square root equals I magnitude squared times x over I magnitude squared times the magnitude of z, which is equal to x over the magnitude of z. So if we put all of this together, we see that our total impedance is equal to z magnitude times the power factor plus j times the square root of 1 minus the power factor squared. And we see that this is going to be, we just have our impedance. This is going to be our V magnitude over our I magnitude. So you see, if at some specific point we're given the magnitude of the voltage, the magnitude of the current, and the power factor, we're really given the whole impedance that we can use, and then we can break this up into a real part and an imaginary part. So this really gives us two equations because we know that the real parts have to be equal and the imaginary parts have to be equal, and that's how we solve for resistances and reactances all at the same time.